In this video, we're going to review the first law of thermodynamics. So the first law of thermodynamics says that energy can't be created or destroyed, it just changes forms. More precisely, we can say that the change in the energy of a system is equal to the net energy transferred to the system as heat minus the net energy transferred from the system as work. And we can write this as delta E is equal to Q minus W. And here, this capital E is the total energy of the system. Q is the heat transferred to the system and W is the work done by the system. And so we'll review each of these concepts a little bit more and looking at heat and work in particular. So heat, of course, heat is given by Q, capital Q, and heat is the energy transfer caused by a temperature difference. So there's many examples, of course, that we could give. Here is, for example, if we have a bar of hot metal, which is cooling in the air. So heat is leaving that bar. Now work, let's look at work in a little more detail as well. So work given by this capital W. Work is the energy transfer associated with a force which is acting through some distance. And this could be a linear distance, this can be a distance that's something is being rotated through. One example of a gas, which is pushing a piston outwards. So that piston is moving some distance in response to the force. And so we can define work mechanically as this integration of force dotted with distance. Now, if the force is constant, then we can take that force outside of the integral sign there, and in that case, then your work is just force times S, where of course F is the force and S is the distance moved, the distance that the force moves that object through. And we'll look at a couple examples here just to refresh your memory about what this can look like. So in example one, we can, for example, push a box with a force of 10 newtons through a distance of, let's say, 2 meters. In this case, of course, the work is equal to that force, which is 10 newtons times 2 meters, which is your distance. So you get 20 Newton meters, which is the same as 20 joules. In example 2, we have a rotating shaft. And here we want to turn a shaft with a torque of tau is equal to 50 Newton meters. And we're going to do that at an angular velocity of omega equals to 3 radians per second. So in this case, we're actually going to calculate the rate of work. It's more convenient. So the rate of work, which is also known as power, is, so W dot to indicate it's a rate. This is equal to the torque multiplied by the angular velocity. And so we have 50 Newton meters multiplied by our angular velocity, 3 radians per second, which gives us power of 150 watts. Now finally, there's one other concept I want to just briefly remind you of, which is internal energy. So internal energy is the microscopic energy associated with molecular motion. So this could be molecular rotation, this could be molecular translation, but the molecules are moving in some way, and so there's an internal energy associated with that, which is a property of the system.